Hi, this is part one of the lesson, Relationships Matter, Evaluating Numeric Expressions. And in this video, we're going to focus on interpreting a number raised to a power and also looking at some perfect squares and perfect cubes. In the past, you've looked at multiplication being an example of repeated addition. So in this example, I have 2 plus 2 plus 2 plus 2, which I can rewrite as 4 times 2. So the 4 tells me I have 4 groups of 2. But what if instead of adding 2 4 times, what if I'm multiplying 2 4 times? That's going to look like this. So if I'm multiplying 2 by itself 4 times, I can rewrite that, but this time I have to rewrite it using an exponent or a power. So when I write a number raised to a power, I have two things. I have a base and I have an exponent. My base is the number that I'm multiplying, and my exponent is telling me how many times I'm actually multiplying that number. So this is why we write this as 2 to the 4th. Let's look at a couple of examples. In my first example, I have a base of 7, and I have an exponent of 5. So I'm multiplying 7 5 times. In this example, I have a base of 4, and I have an exponent of 8. So if I were to write that out long ways, I would have 7 multiplied by itself 5 times, and I would have 4 multiplied by itself 8 times, which would both be very large numbers. I can relate powers to some geometry work you've done in the past. So I know that the area of a rectangle can be found by multiplying its length and its width. So the area of this rectangle is length times width. A square is a special case where the rectangle has all the same side lengths. So I can call this side S and this side S, and I still multiplied those two lengths to get my area. But since they're both the same, I can write that as just side times side, or I can write that as S raised to the second power. You'll often hear us say that this is S squared because it's the area of a square with a side length of S. That also comes into play when I'm looking at volume. So the volume of a rectangular prism is the length times the width times the height. A cube is just a special case of a rectangular prism where the length, the width, and the height all have the same length, so they're all can be represented with the variable S. So I can say that the volume is S times S times S, or S to the third power, which I can also read as S cubed, because it is the volume of a cube with a side length of S. So you'll hear us say S squared a lot. You'll hear us say S cubed a lot. Let's look at a couple of examples. So if I'm finding the volume of this square and the length is 9, then I know that I'm simply going to say that my area, I said volume, I'm looking for area, is 9 times 9. Or I could say that the area is 9 squared. So my area is simply 81 square centimeters because it's 9 times 9. And square centimeters because I measure area in square units. If I'm looking for the volume of the cube, I'm going to say that my volume is 2 times 2 times 2, which I can also write as 2 raised to the third power, which I can also read as 2 cubed. So my volume would be 8. And here I'm going to be measuring in cubic centimeters. So it's 8 cubic centimeters. There are special cases of numbers that we call perfect squares and perfect cubes. Let's look at perfect squares. 9 is a perfect square because I can write it as the product of a number times itself, where that number is an integer or a whole number. So that would be the example of this square. The area of this square is 9, as the area is 3 times 3, or 3 squared. 9 is the perfect square. 16 is also a perfect square because I can write 16 as the area of a square with a length of 4 on each side. 4 is the same as 2 squared. It's a perfect square. 5 is not a perfect square because if I had 5 of these, I could not make a perfect square without cutting one of those apart. So my perfect squares are numbers that give me the area of a square that has an integer side length. So if I think about a perfect cube, I'm looking for a number that could represent the volume of a cube where the side links are all whole numbers. So 216 is equal to 6 cubed. So 216 is a perfect cube. I can also think about modeling these expressions using pictures in another way. So if I think about modeling the expression 3 times 2, I can use an area to represent the fact that this is just a length of 3 and a width of 2. So my area represents 6. So how would I model an expression like this? These two expressions are very similar, but they involve squares. So this would be 3 squared plus 2 squared. This would be the quantity 3 plus 2 squared. So you can hear it and you can think about what I'm saying and what you're hearing and how that picture should go along with it. So 3 squared plus 2 squared is literally 3 squared plus 2 squared. It's a square with the side of 3 plus a square with the side of 2, which would be 9 and 4, which gives me 13. This quantity 3 plus 2 squared means that I want to add these two numbers together and create a square that has that length is the sum. So this is a square with a side of 3 plus 2 and a side of 3 plus 2, which is a 5 by 5 square, which gives me an area of 25. So this would be 25. Let's look at a volume example. These look very similar to the squares, but this is the sum of two numbers cubed. This is the sum of two cubed numbers. So this is 3 cubed plus 2 cubed. This is 3 plus 2, the whole quantity cubed. So if I look at a picture for that, here I can see a 3 cubed and a 2 cubed. Here I see something that's been built by adding 3 plus 2 together. So this would represent 3 cubed plus 2 cubed, which is 27 plus 8, or 35. This would represent 5 cubed, or 5 by 5 by 5, which would be 125. So thinking about squares and cubes in terms of the powers helps us also think about the model. So let's do a quick recap. We looked at how we can write something that has been multiplied multiple times by itself as a power, what the base means and what the exponent means. So you're ready to look at a number that's been raised to a power and rewrite it as a multiplication problem, or you can look at a multiplication problem and write it as a power. You can also go in and think about what are perfect squares and perfect cubes and what those numbers mean. So in the next video, we'll look at simplifying numeric expressions that actually include a lot of powers and parentheses. So I'll see you then.